Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast. And my guest today is Philip Bourne. He's the Stevenson Chair of Data Science, the director of the Data Science Institute, and a professor in the Department of Biomedical Engineering at Virginia. So, Phil, looking at your bio, it's so extensive, it probably would be better if I asked you more about your background directly, but I want to welcome you first. So thanks for coming on the podcast.
Oh, pleasure. Thank you very much.
Yeah, tell me a little bit more about your background, because I can see it's super extensive, and maybe you can relate it far better than I could.
Well, that just means I'm very old. I actually was born in the UK, and I grew up in Australia, so which means no one understands me at all. But I did all my undergraduate and graduate work in Australia. I have a PhD in physical chemistry, which is very little to do with what I do these days, but that's the way it goes. I then went on to postdoc my PhD was really looking at crystallography and structural related materials, particularly organic compounds. And then I went to the UK, the University of Sheffield, and I worked on biological macromolecules. So I was working, actually trying to understand we looked at ferritin, which is a body's iron storage protein. So we were trying to understand the structure-function relationship, particularly as it relates to different diseases in iron metabolism. That was a lot of fun. We learned a lot about iron metabolism, and during that, very interesting molecule. It was the early days of this sort of macromolecular crystallography, so it was quite challenging in those days. Then I went on to Columbia University in New York, where I was working on, again, structural biology, but postsynaptic neurotoxins. And then my life took a fork in the road, and I was complaining to the dean in the medical school about the state of computing at Columbia. And he said, well, what would it cost us to fix it? So I said, well, start with $1 million and we'll go from there. I ended up running a computer center in for the medical school. So that was sort of a divergence. I published several books on computing and things like that. And then, I don't know if I'm going on too long about this, just cut me off. And then, I got intrigued by the whole notion of the Human Genome Project and how that was very tied to computation. And we developed algorithms for sort of assembly. And that sort of, opened my eyes to what was really going to be the future of, in my opinion, of biomedicine, which it was going to become, and it took quite a while, but it was going to become very computationally driven, very analytically driven. So, I kind of pursued that, decided that was not the best place to do that kind of work. So I went to UC San Diego, where I was there for 20 years. I particularly studied systems pharmacology there. I was involved with running a resource called the Protein Data Bank, which was a sort of a collection of all this structural information, at least. And then I got interested in what you could do with from the point of view of translation into the private sector. I formed a number of startups while I was there, and that then led me to becoming the Associate Vice Chancellor for Innovation. Then went from there to be which I can talk a lot more about, but I get a sense I shouldn't go on too long about this. I was the first Chief Data Officer of the National Institutes of Health. And then a year and a half ago, I came to the University of Virginia, where I'm developing a whole data science institute and an initiative across the whole of campus.
So the most outrageous question you ever could be asked by the scientific community is, what have you done for us lately? Because you've done so much. But speaking of which, what's your current initiative? What's your fascination right now? What are you working on?
So I've kind of broadened away from just biomedicine, and I'm really intrigued by the whole development of data science, which is kind of what I've been doing to some degree all along. So it sounds a bit silly, except it's really reached the mainstream. And I think the excitement is that it's bringing data together from disparate sources to do things that sometimes are actually unimaginable. And there are new algorithms and improved, some of which have been around for a long time, but they've improved. We've got these graphical processing units now, which are much faster computing capabilities. So it's really opening up, and frankly, it's beginning to what's driving modern society. Companies today can't, unless they're analyzing their own data and making decisions within their companies based on what they're doing, what their own data is telling them, they're falling behind. So it's it's a huge opportunity, and we're churning out graduates that just they get jobs months before they graduate with outrageously high salaries. So it's kind of just a very interesting time.
Well, the field is really expansive. So what area in it are you focusing on? There's
the institute I run it actually covers everything. So everything from digital humanities, social sciences, to biomedicine, of course, to engineering, financial, transport, energy, you name it, environment. We have projects going on across that whole space. And what's really interesting is when you combine data from different sources. So, for example, I'll just give you a quick example. When we're looking at, we've been exploring ozone levels in the Blue Ridge Mountains here in Virginia, and that's done from static, sensors that sit on poles in the mountains here. Well, some of our students who love working with drones essentially managed to mount them on drones, deal with vortex issues, and now gathering geospatial data across whole environment. So we've combined engineering, computer science, and environmental data to learn new things about ozone levels across many different terrains, which would have not happened without bringing these students together from different, from computer science and environmental science. So that kind of stuff is, for me, really exciting.
Okay. So what do you see that data science needs in order to be more effective? I mean, I guess there's a couple things happening. Is now more and more sensors are out there and more data is being collected, but I'm not sure if the interpretation of it is going to keep pace with it. Again, I'm only one person, but it just seems like there's so much data out there. Who's going to analyze it all? Who's going to look at it all? So it seems like it's just an abundance of it that something needs to be done with.
Yeah, I mean, I think there's lots of issues surrounding the data. I mean, we're building ourselves on 5 pillars, so the first pillar is data acquisition, which, as you say, there's no end to the sources of data. There's often lots of issues surrounding that data. And then the second pillar is data engineering, which is really a major component of at least where you spend the time, which is, really munging the data to get it into a usable form. And, I think one of the ideas that we have here is the notion of open data. So when we do that, we give that back to the community. So that already is a big step up in the sense that this data has been vetted and analyzed and documented in some way, and then it's findable. So we have a notion of an open data lab doing that. And then the third pillar is this, the actual analytics, and clearly machine learning, various types of machine learning, natural language processing techniques are allowing us to do much more. And then there's the visualization and dissemination. And then there's the ethics, the final pillars, the ethics, policy, and law associated with how we use data and so, all that, the whole Facebook, privacy issues around health data and so on.
Okay.
So, there is, I think we work in accordance with what we call the FAIR principles, which is the ability to find, access, interoperate, and reuse data. And of course, we find a lot of the data, a lot of what we look at doesn't conform to the FAIR principles. So, to your question, it is a problem. And I think over time, you start to see quality reference data sets appear, which have a lot of value, and it actually makes you think about what's valuable within the academic system here, where what's more valuable, a paper that no one reads or a well-formed data set that 100 people use. The problem is that the system of reward does not necessarily reward that good data set, but they'll reward a crappy paper. So what can I say? The system's broken.
Well, what about in the interpretation of the data? Even when it is interpreted, like you said, data science is in high demand. So what are some things that confound data or confound the analysis of it? What's important?
Yeah, well, there are lots of confounders, and often it's not clear what features you can do so-called unsupervised learning. So you're not actually sure. You might get some results, some form of clustering of the data, but you don't really know why that happened. So there's a lot of danger associated with that. On the other hand, if you actually sort of do feature selection, so you're really doing supervised learning of some form, then you don't necessarily know you're looking for the right thing. So it's a tricky situation. I think the key is, and this is where I think what distinguishes data science from other forms of, say, computer science, is that data scientists are typically trained to work in a specific domain, so they understand something about the data that they're analyzing and whether the results, in fact, have some form of meaning. And I think that knowledge is really critical to be effective in using this kind of data. So when someone asks me that, to me that's some sort of distinguishing feature. It may not be that they're developing the algorithms, they're just applying them, but they understand the implications of that application in a certain domain. It could be biomedicine, but it could be others, of course.
Are there yet off-the-shelf data analysis packages that work with all kinds of data to make it easier for people, so they just have to worry about collecting it and then connecting it to off-the-shelf packages?
Yeah, I mean, there's the extent of MATLAB, R, and Python tools, which are the sort of bread and butter of data science. There's lots of tools that do all sorts of things, everything from deep learning to various types of regression and so on, statistical methodologies. So there's a lot of tools out there, and that's, I think, something else that's propelled the field. That combined with resources like GitHub, which actually enable people to search and find code and essentially use code that's been to some degree crowdsourced. These are all really positive developments. And then things like using Jupyter notebooks to actually document and embed code into from the point of view of creating a reproducible framework for the work is, I think, another example that of where things are headed, which I think is very important. So there is this coalescence of knowledge around tools and data and platforms that support all of that. So I think it's a time, it's definitely a different era because of that.
You said that society, whether we know it or not or like it or not, I guess is being run by data. So, what evidence do you see that points to that? What's interesting to you that jumps out at you now that you're in this field?
Well, I mean, the obvious ones are the things we read about in the newspaper, which are things like, what you can learn about someone, from what Google know about people from what they search. They know things that loved ones don't even know by virtue of the searches that people conduct. And that's just the tip of the iceberg of social data that's actually gathered and used, which of course is what gets all the attention. But we just Amazon have just announced that they're opening they're part of their second headquarters here in Virginia. And if you imagine just what companies like that do, I mean, the whole productivity of the company is built around data analysis and how they move packages around, how they actually define how you purchase, what you purchase. All of that data is being collected and used, and that's again another fairly obvious example. I'll give you a much less obvious example, but one I like a lot because it says a lot about the field. So not that long ago, a trauma surgeon came to see me in my office who works here in the medical center, and he was asking me about various aspects of data science because what he noticed from doing trauma surgeries over the years, many of which are related to car accidents, that there's he noticed a correlation between the type of accident and ultimately what was discovered about the type of internal injury. Well, the problem is when someone comes into the emergency room, you don't necessarily, these injuries are internal. If you don't know anything about the accident, it's hard to know how to begin the treatment. So you basically do a full body scan, and occasionally patients die in the scanner. If you knew what kind of accident they'd been in when they arrived at the emergency room, you might be able to intervene in a different way. So he's been trying to look at this from a quantitative way. He went to the Department of Motor Vehicles, got a whole bunch of public data about accidents in Virginia, then correlated that with information he had access to in an electronic health record, and indeed found correlations, or is finding correlations. He now wants to take that to the next step. The idea is making intervention so that when someone shows up in the emergency room, the emergency services have already radioed ahead or videoed or texted or whatever it is, the kind of accident that took place. And so the treatment regime would be based on this, this predictive modeling.
Yeah, I see you'd want to get data, if you could, directly from the car itself at some point, so you could see all the parameters of the accident.
Yeah, well,
that's that with the hospital,
Yeah, absolutely. And in fact, of course, they don't want to reveal that information. Most cars now have a black box that, I wouldn't say it's quite up to an airplane standard, but it records a lot of information, acceleration, deceleration, particular movements that would indicate a certain type of accident that would be very useful in this regard. Unfortunately, that data like that is coveted by the company, partly to improve their own product, but partly to protect themselves, probably, which brings in the whole ethical question.
Yeah, what else do you know about data that other people don't know? Or, maybe you could talk about, a few other projects, what's really interesting to you about them, data-wise?
Well, my own particular research interest is in using proteomics type data, which is data on proteins and things of that nature. So and we try and apply it in the context of drug discovery. So one of the way drug discovery and drugs have been designed for many years follows what was called the Ehrlich notion of one drug aimed at one target, typically a protein in the body, and with having one effect, which hopefully is a positive effect on a particular health condition. Well, of course, it turns out you only have to listen to the commercial on the televisions. When you hear the reaming off the side effects that come from drugs, you know that that's not actually what's happening at all. In fact, what's happening is that drug is actually binding to a number of these protein receptors and having some kind of collective effects on a complex system. And so the more you understand about that complex system, which involves collecting data at different biological scales, the more you can do to design drugs that actually mitigate side effects as much as possible. So in that case, you're collecting data from the genomic level all the way up to the level of the individual, and so this brings into play the whole notion of precision medicine, because first of all, not only there's side effects that everybody has, there's also side effects that only certain people, whether it's related to gender or ethnicity, or actually even body mass and other kinds of things that get affected. So this idea of one treatment for all is just not right, and we're now refining what we do and how we think about this. And that notion of precision you can apply not just to medicine, but you can think about it in precision education. Effectively, in a very coarse way, we all get the same kind of education, and it doesn't cater to our individual needs. But as we start measuring more and more data about, say, students in the classroom, including, everything ranging from individual transcripts, performance, to just things like measuring eye movement of students and how attentive they are to what the teacher's saying. These are, it's more data that's starting to be collected, at least in a research environments, to see how effective these kinds of data are. All sorts of things can be determined from that. But, there's obviously a lot of privacy and implications surrounding that. But those are just a couple of other...
That's what I was going to say. That jumps out at me. There's data that you create where it comes from you, and that's, I guess should be personal, but it also has an element to it that can contribute to the greater good. So it sounds like data rights are going to be hugely important. And depending on the type of data, you wonder who's going to have rights to it and how. And like the car example, could the government or should the government compel car manufacturers in case of an accident to provide that data, immediately, have a back door for them so that it could be provided to medical, people that treat them medically.
Yeah, you're absolutely right. I think there's this balance that we've yet to really come to grips with between the good and the bad that comes from data, or can come from data. And, in the end of the day, I think it's, we don't even know, if I'll ask you, when you go to the doctor, and you have some kind of test that's returned in electronic form, who owns that data? Is it you?
It seems like them, because it's hard to get from them at all.
Well, is it the insurance company? Is it the care provider? Is it who the care provider works for? Is it the patient? It's not. These things are not necessarily very clear at all. And in fact, you have a right to a copy of your data. That's essentially part of HIPAA. But what they, and there's obviously consenting for use of that data for other purposes. But in terms of who owns it, it's not necessarily clear. And you can imagine, you can say that with regard to many different types of data. So I think the kind of legislation that's coming from Europe now, I think begins to sort of address these kinds of questions. But we've got a long way to go.
Definitely, yeah. Any from your data on proteins, proteomics, I guess you called it, any surprises or really amazing insights, or maybe other projects you worked on, things that just are really interesting conversation for you to talk about?
Well, not so much in what I described to you with respect to drug discovery, but I'll give you an example from evolution. It's absolutely remarkable that proteins consist of what's called amino acids, and you can think about them, if you're not a biologist, you could think about them as like beads on a string. And a typical protein is 300 of these beads. And those beads are of 20 colors, because there's 20 different types of amino acid. So that's 20 to the 300 possibilities. That's more than all the atoms in the universe. And yet we know all we've discovered on Earth so far is about, I haven't looked recently, but the order of 40 million individual types of proteins. So that's one tiny, tiny fraction of all possibilities that are found in life. Then what's even more remarkable is that those beads on a string, that linear one-dimensional string, actually folds up into a three-dimensional structure. That's what a protein is. And it's that structure-function relationship that is important. Interestingly, those 40 million or whatever it is individual proteins we've discovered fold up into about 1,200 different shapes. So all of life is comprised, you can think of it this way, of 1,200 different jigsaw puzzles, pieces. Everything on planet Earth is derived from those pieces. So when you look at that in the context of evolution, inventing a new puzzle piece is a major step in evolution. And we devise ways of actually looking at when and how new puzzle pieces were, let's just say, invented by nature. And we discovered a strong correlation between that invention and changes in the environment. So when the Earth evolved from a reductive to a eugenic to an oxidative environment and became oxygen rich, what the kind of proteins that were formed and how they were used in life changed. And so what this tells you is that the environment has a pretty distinct impact on life, and it's not just over very long time scales. It can happen in bacteria in very short time scales. So you look at cyanobacteria in the ocean that, say, are near the mouth estuaries of rivers that are flowing metal deposits or from industry. That changes the nature of that life. And so the implications of this are pretty huge. And then the life in turn can affect the environment. So there's this crazy notion of the Gaia Hypothesis back in the 70s, which is sort of the yin and the yang, where life and the ecosystem and the environment are sort of combined into one rich system. And this starts to show it. So I don't know. We worked in that a number of years ago. It was really cool, I have to say.
Well, I know it's maybe off subject, but I wanted to ask you a couple of questions about proteins. So for a protein, can it fold three-dimensionally only in one way, or can it fold in different ways and therefore act differently?
Well, what's interesting most of the time, and this is actually one of the unsolved problems of, it's not quite as unsolved as it used to be, of molecular biology, is that if you denature a protein, so in other words, say you heat it up and you destroy that three-dimensional shape, if you renature it, that is, if you cool it down, it will assume typically speaking, it will assume that same shape. So everything inherent in that shape is embodied in that one-dimensional sequence, that particular sequence. Wow. The problem is that given this redundancy, that you cannot tell that two proteins, they diverge so much in sequence, and yet they still fold up into the same shape. So the question is, can we actually predict what that shape's going to be? This has implications for protein engineering and things like that. If we could engineer proteins, so in other words, if we've only occupied a small fraction of this potential space, fold space that nature could have adopted, why haven't we? Are there stable proteins that we can engineer that nature hasn't, that could have implications in healthcare, in environment, in food growth, goodness knows what else, in energy? And, I think the answer is probably, certainly such proteins have been engineered. And so I think it offers enormous potential for the future if we could understand more about this relationship. And it may be that deep learning, so it's very interesting that this was just a snippet in the newspaper a year or so ago when Google announced AlphaGo, which was their deep learning based AI technology, was actually not only initially able to beat the world's best Go player, but then they built a version of the software that actually learned not from the Go players, but it learned from the previous algorithm and actually beat the previous algorithm. And so it's, this powerful machine learning tool. And right at the bottom of this newspaper article about this and now this algorithm is being applied to the protein folding problem. So in other words, can we learn from what we know in nature already to actually solve this long-standing problem in biology? The answer's still out, but we're looking at it in our own way. But a number of other researchers are doing the same thing.
Amazing. Well, very good. I mean, there's a lot more to possibly talk to you about, but for now we're out of time. So what's the best way for interested parties to reach out and to engage with you or the lab or some of your projects?
Probably by email. So my email is peb6a@virginia.edu.
Okay. Well, very good. Well, Philip, I really appreciate you coming on the podcast. It's been really interesting.
Sure. Thank you for having me.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.